Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 3 of module 10. In the module 10, we have been discussing about earthquake geodesy. In the lecture today, we will cover the following concepts such as the geodetic, seismological studies. Those will be combined together and we'll see how the rupture process can be obtained using seismological data and how we can obtain the auxiliary plane and the nodal planes of the earthquakes using the geodetic data. And then we will be discussing about after slip and the post seismic slip. As far as the recap of previous lectures are concerned, we talked about geodetic methods using signals from space that can permit to identify all the three components of a position that can be measured to sub-centimeter precision. Then we said about the popular geodetic techniques to measure ground deformation. Those are very long baseline interferometry. In short, it is known as VLBI. Then we understood about the satellite laser ranging, that is SLR. And then finally, the most popular one is the global positioning system, that is the GPS. GPS that uses the constellation of the satellites that can transmit coded timing signals on a pair of microwave carrier frequencies that are synchronized to very precise onboard atomic clocks. And then the GPS data can be collected in two modes. One is the continuous mode, another is the survey mode. In the survey mode, we install a GPS at a particular location for a shorter period of time. Then we revisit the place after some time. That is how we recollect the data. And then in the continuous mode, we keep an instrument for a longer period of time at a particular place that collects continuous mode of data. The later one, that is the survey mode, is much cheaper than the continuous mode of data collection. The limitation that the geodetic data collection imposes is the position of the geodetic marker, because the geodetic marker position should be at a anticipated location of the earthquake, that is can be probably in the region of high seismicity or the active regions. Then we talked about the resolution that can be achieved using the geodetic data, such as the data from INSAR, where the radar that is having the antenna length of d and the distance or the altitude is r, and the earth's surface on which we can resolve the object of size x can be given by theta d, that is equal to lambda by d is equal to x by r. The phase difference between the radar signals with wavelength lambda reflected from the earth's surface and recorded by antennas at position A1 and A2, the phase difference is given by this particular expression phi, that is equal to 4 pi by lambda r2 minus r1, where r is the range from the antenna at AI to the reflection point. If the differences between the satellite are removed or the differences between the positions of the satellites are removed, a vector surface displacement d causes a phase change, that is phi is equal to 4 pi by lambda delta r, where delta r is d dot r cap and delta r is the projection of the vector displacement along the look direction connecting the satellite and the reflection point. Then in the previous lecture we studied about the static co-seismic displacement that contains 1 by r square term, that if we compare it with the 1 by r term for the propagating waves, then it decays more fastly with distance from the earthquake. For the infinite length fault, the fault parallel displacement in x direction, that is uy, can be given by from this expression, that is uy is equal to plus minus dy2, that is d is the slip on the fault plane, minus t by pi tan inverse y by w. W is the width of the fault and y is the direction perpendicular from the fault location. For the finite fault, the formula will change to this expression, and in case of finite fault where the fault is buried, then we have an extra parameter, that is w, that is the depth of the fault from the surface. Sometimes the buried fault is also known as the blind fault, because the expression of the fault is not appears on the surface, so it is known as the blind fault. A fault that does not reach the surface, the displacement is both reduced in amplitude and varies more smoothly with distance than it would for a fault extending to the surface. Estimation of fault parameter using geodetic data is an inverse problem and has highly non-unique solutions. So that is why it is considered that we generally inverse the geodetic data combined with the other kind of data such as the seismological data, so that we can have better constraint on our modeling process or the search space, and then we can find out a better solution having a lesser number of acceptable models. Now, if we start with the lecture today, the first thing that we must understand about the joint inversion. We are going to talk about the joint inversion of the geodetic and the seismological earthquake data. First, we go into the deep into this particular topic. First, the thing that we need to understand is the need of it, that is why it is needed to do joint study. If you want to understand joint inversion or the joint modeling processes in a simpler day-to-day life processes, then let's suppose I will ask you to find an address in Dhanbad, for which I will give you some parameters. Well, let's suppose I will give you that, okay, there is a particular house which is located in the southern part of the city of Dhanbad. Then there are many possibilities, and the parameter, that the constraint that I have provided you, the southern part, that means south. So there are millions of houses in the southern part of the Dhanbad city. Now, if I will give you one more parameter, one more information that may be used to constrain your number of addresses that are in the southern part of Dhanbad, I will say, okay, in the southern part of Dhanbad there is an area with the name Bank Mode. Then you can identify and go there to that place. Then your number of solutions will be limited to a very few number of addresses. Then again I will give you one more parameter or one more constraint, that it is located in a particular street number 2. Then your number of solution will further reduce. That means you are going to have, in the first case, when you were just given a parameter southern part of the city, you will be having the many possibilities, millions of possibilities. Then as soon as I added one more kind of data set, that is I have said the bank mode, then your number of possibilities has reduced significantly. And then I have given you one more parameter, that is the street location, that means the street 2. Then your number of possibilities has reduced much further. So that is how what we are doing. We are complementing the entire process by incorporating more and more kind of data set. First data set was southern, second data set was the bank mode, third kind of data set was the street. In the first case, you were having the million number of possibilities or the million number of solutions. In the second case, you were having only maybe the 100 number of solutions. And then in the third case, you will be having maybe 10 or 20 number of houses in the street number 2. So what we have done, we have complemented the process by incorporating the different type of constraints provided by different kind of data set. So that is what we are going to talk about in the joint study of the geodetic and the seismological earthquake studies. So that is what it is written here. Estimation of the fault parameters using inversion of the geodetic data alone is highly non-unique. That means there are many number of possibilities for the fault parameters if you do inversion of geodetic data only. If you are going to use the geodetic data only, then number of fault parameters will be significantly large, that will add to the non-uniqueness of the solution, because many number of solutions are possible. That means non-unique solutions are there. In case if you have one more data set such as the seismological earthquake data together with the geodetic data, then your solution may improve. The process will be complemented to each other. So this is what it is written: joint inversion of geodetic and the seismological earthquake data may prove to be complementary to each other. The third point is seismic waves are unable to distinguish between the fault plane and the auxiliary plane. Now we are going to talk about the sensitivity of the individual kind of data set. So the seismic wave generally are unable to distinguish between the fault plane and the auxiliary plane, but this thing can be done or easily identified by the geodetic data. On the other hand, seismic data can provide the constraints onto the rupture process of the earthquake mechanism. So both the things are complementary to each other. The seismic data alone cannot distinguish between the fault plane and the auxiliary plane, but that can be easily done by the geodetic data. On the other hand, geodetic data cannot provide you the information about the rupture process, but that can be easily done by the seismic wave data. So if we model both the data together, then we can have better constraints on the fault geometry and can identify or can find the slip in a better way. So this is what it is written here: joint data give better constraints on the fault geometry and slip on it, and inclusion of aftershock location may provide even better constraints on the fault dimension. Apart from having both of the data together, if we add aftershock location as well, then we can have way better constraints on our modeling process, and it will lead to give you the better idea about the fault dimensions. Now, if you look at this particular example where both kind of data sets such as the geodetic and the seismological results are being inverted together or modeled together. In this particular figure, the earthquake of 1994, that is famously known as Northridge earthquake, happened in California, has been taken as an example, which occurred on a buried thrust fault, or you can say blind thrust fault. Using the focal mechanism, you can see this is the example of a focal mechanism here, and aftershock distribution that indicate the faulting on a northwest striking and the southwest dipping fault. So you can see this is the fault mechanism, and this is the fault mechanism beach ball diagram for a thrust fault or the earthquake that is happened on a thrust fault, and its strike is in this direction, that is indicated by red color line, and the dip direction in the southwest direction, that is indicated by this blue arrow. Now if you look at this particular diagram, which is basically indicating towards the GPS motions, or you can say the static displacement or static deformation. The static deformation is indicated or represented by the bars, that is, if the motion is high, then the bars are higher. If the motion is low, then the bars are lower. If the motion is in the negative direction, then the bars are inverted. So if you look at these bars here, this is just above the fault location. These are much higher than the other locations that are represented in the other places. Likewise, if you look at, if the fault is located in this direction here, then the block that is into this particular area, then this particular area is the hanging block, and this hanging block is moving up. That means it is moving in this direction, right? So if you look at the direction provided by the GPSs, the direction of the GPSs are also in this particular direction, and this is what we were expecting from our modeling results. And also, if you look at this particular diagram here, this basically represents the aftershock locations, and in this diagram we have modeled both of the data together, and those are providing very good result if we are considering the 2.5 meter of slip that is occurred on a fault plane similar to that which one would infer from the aftershock. So there are two models. One is having the uniform slip on a smaller fault, that is this one, and there is a longer fault that is having the variable slip. So both of the models are providing better results, good results if we model both of the data together. And this is the location of the main shock. Now let's take a look at combining the seismic data and geodetic data. Seismic data, we are now having the strong motion data and the teleseismic data, both of the data together, and also the geodetic data for the same earthquake, North Ridge earthquake. Now strong motion data can provide you the details of the high frequencies for a source time function and can be further utilized to understand the slip process. And if you look at the teleseismic data, then such details are not possible in case of teleseismic data, or you can say those details will be ambiguous and will not be provided by the teleseismic data due to the attenuation of the teleseismic waves. The slip distribution has been represented in these figures, and if you look at these figure, first figure is basically provide the slip distribution using only the strong motion data, and this is for the teleseismic data, the slip distribution, and this is using only the geodetic data alone for finding the slip distribution. And if you look at these results, the result from these different type of data types are basically very variable, or you can say very different. And the seismic data basically can be used to resolve the slip during the rupture process only. Both seismic data like the strong motion data and the teleseismic data are used to yield the high slip onto the northwest corner. If you look at this diagram and this diagram, and both of the data are providing the high slip in the northwest corner in this particular location. And on the other hand, if you look at the slip distribution using the geodetic data only, the geodetic data provides much smoother image in compared to the strong motion data and the teleseismic data, and that basically depends upon the end results. That means the geodetic data do not provide the slip during the earthquake, but it can provide the pre-seismic time or in the post-seismic time, and this is smoother in this case. If we combine both kind of data together, seismic data and the geodetic data, then how the figure will look like, or how the slip directions will look like, it is given in this particular figure. And this basically provides much constrained slip distribution process, and you can see that the slip is higher in this particular area, and this is the location of the epicenter. One more thing that I would like to add, that the largest slip is not happening at the location of the epicenter, but it is happening much further away from the location of the epicenter. So but still you can say at the epicenter location the rupture might have started, but the slip is happening in the large amount in the northwest direction, in the northwest corner, like this and this. And even if you combine both the data together, then also it supports our claim that slip is happening in the northwest corner of the study area. Now, if you look at the earthquake catalog data, or you can say the seismic data and the geodetic data that are taken from the GNSS observations, then you can see how the flow process for the processing of both the data types looks like. Then if we talk about first the GNSS observations, then the GNSS observations, that means the geodetic data, then GNSS observation and the supporting files that we are first trying to have, then we perform the processing of those data, then we try to extract the coordinate and convert those coordinate to the universal transverse Mercator coordinates, and then we remove the outliers, and then we plot the time series, and then we have the displacement and the velocity computation, and then the strain computation. While on the other hand, for the earthquake data, we have an earthquake catalog, The earthquake catalog may be consisting of different kind of magnitudes such as the surface wave magnitude, local magnitude, body wave magnitude, coda wave magnitude, and maybe the moment magnitude. But most suitable magnitude scale is the moment magnitude scale. So you will have to convert other magnitude scales available in the catalog to the moment magnitude scale, that is represented by m in subscript w. Then we perform the declustering process, because in the catalog, apart from the main event, you will also be having the foreshocks and the aftershocks. So you need to remove the dependent event, those are aftershocks and the foreshocks. So removal of those events is known as the process of declustering, and so we need to perform that declustering process. And then after, we need to estimate the magnitude of completeness. So magnitude of completeness is the minimum magnitude above which the catalog is considered to be complete. So this is the minimum magnitude, that is represented by MC. Sorry, it should be C. So magnitude of completeness estimation need to be done. So thereafter, we will be performing the B value estimation, and this B value is very important in the case like if suppose the B value of an area is high, that means the smaller magnitude earthquakes are more susceptible in that area. If it is lower value, then it is the area is more susceptible for the higher magnitude earthquakes. And then after you do so, then both the data will be reclassified, and then we may assign weights according to the sensitivity provided by both of the kind of data sets, and then finally we will use our results in identification of potential seismic zones. Now let's understand the rupture process, or you can say the time evolution of the rupture inferred from the waveform data. Here we are not going to talk about the geodetic data, we are just trying to look at the time evolution of the rupture, how the rupture is evolving with time, that we are going to talk about, and that these results are found using the waveforms data only. So this is what it is written here. Time evolution of the rupture process is shown in the figures below and in the following slides. These are inferred from the seismic waveform data. Since these are sensitive to the rupture process of an earthquake, rupture began at the epicenter. So if you look at this figure, then this is from 0 to 1 second at the happening of the main event. This is 1 to 2 seconds after the happening of the main event. This is after 2 to 3 seconds, and this is 3 to 4 seconds. Here we have after 4 to 5 seconds, 5 to 6. Likewise, up to 7 to 8 seconds, we have these evolution of the rupture. And you can see the rupture has started at the epicenter location, and then it started to move in the up dip direction. So this is the up dip direction here. So the rupture has started to move in this direction. So it is moving in this direction, and then it is again moving. So it is keep on moving in the same direction, and then after that it moves in the northwest direction like this, and then finally it settles itself in the northwest corner. So this is very, very nice picturization of the rupture process, where we can see how with time the rupture is evolving. So first it was started at the epicenter, then it moved in the up dip direction, then it is moving in the northwest direction, and then finally it settles at the corner of the northwest corner. So if you look at these figures are basically giving the best look to date into the rupture process, and are being combined with experimental and the theoretical studies of the rock fracture to explore the complex physics of the earthquake faulting. So this is just from the seismic waveform data. But if we combine it with some experimental and the theoretical studies of the rock fracture, then we can have much better view of the rupture process, and that is a very complex phenomena, or you can say it actually involves a complex physics of the earthquake faulting. Now let's understand about the after slip or the post seismic slip. So geodetic data after earthquakes also sometimes show a phenomena called after slip or the post-seismic slip. And the deformation happens very rapidly during the happening of an earthquake. Thereafter, it basically slows down a little, and then deformation goes on silently for some time after an earthquake, and it's seismologically observed aftershocks. So after the earthquake, when the deformation is happening silently, then the deformation happens with the happening of the aftershocks. And for plate boundaries, this motion is sometimes thought of as a post-seismic portion of the seismic cycle, during which the motion slows from the rapid co-seismic motion to the slower interseismic motion. If you remember the seismic cycle, there were 4 stages and the phases. First was the interseismic stage. Second was the pre-seismic stage. In the pre-seismic stage, the foreshocks happens, and there was another phase that was co-seismic phase. And this is the phase when the earthquake or the main shock itself happens, and thereafter we have the post-seismic phase. In the post-seismic phase, aftershocks happen, and then after the seismic cycle starts again from the interseismic stage. So this is what it is written. For plate boundaries, this motion is sometimes thought of as a post-seismic portion of the seismic cycle, and during which the motion slows from rapid co-seismic motion to the slower steady interseismic motion. It is often unclear whether the post-seismic motion reflects continued slip on the earthquake fault or not. This is the summary of today's lecture. Seismic waves have an ambiguity in distinguish between the fault plane and the auxiliary plane. The geodetic data do not show the static displacement models and can be used to identify the nodal planes that are perpendicular to the fault plane. We use strong motion data, teleseismic data and geodetic data that provides good constraints on the fault geometry and slip on it. Geodetic data that depend on the difference in the position before and after an earthquake provide no information about what happened during the earthquake, whereas seismological data provide complementary information, can sometimes show how the rupture evolved. The result for the different data types differ because each is sensitive to the different features of the slip. In the post-seismic slip, deformation goes on silently without a seismic signal for some time after an earthquake, and it's seismologically observed after shocks. These are the references for today's lecture. Now we will meet for lecture 4 of module 10. Thank you so much. Bye-bye.